first time that you press build the diagram is gonna take a lot of time. Okay, after the simulation, the Wincom is gonna give us this window, Wincom server.
After building it.
After building, and then we just need to open the two outputs that we have in the code. And remember, we need to do some changes with the buffer. This window is gonna get the tachometer output, and this one is going to get the encoder output. So for the tachometer, let me change the y-axis. It's gonna be the y, just the y-axis, from 9 to -9. And the encoder are gonna leave right like that because the value is gonna be really small. So
it's gonna be really big.
Really small. Oh, really big.
Yeah, so it doesn't fit anyway. But if you do an auto scale later, it doesn't matter.
Oh, yeah.
And as long as your buffer size is big enough, all the data is saved, although it may not be shown on the screen.
Okay. So. Yeah. And we are ready to build the program. So just remember to press this button. It's gonna run the program. It's going to show you the output.
And one thing to note here is the reason the tachometer output is negative and the encoder is going positive is because based on the direction of rotation of the motor, the encoder is inverted in this case. That's why it gives you negative outputs in one direction and positive in the other. Accounting for the sign is essential, otherwise it will mess up your system.
And remember, if you cannot see the value of the tachometer, you just go to Access and press Auto Scale, and it's going to show you the value.
So we just let the loop run and do it for all the amplitudes, and then we can run our code and do the math on it.
Yeah, now it's done. So after that, because we have the data already saved, we just need to write a program using the same amplitude array that we have before, and using also, we need to open for each value of the array. Is gonna be j. We have to open the tachometer output and the encoder output. So after that, we just need to load for each value. Remember, for each value of the j, we need to open the response of the encoder and the tachometer as well. After that, we just need to do some calculation. We need to, in this Lab1, we need to calculate the count per second. The count per second is going to be the encoder data, the last value of the encoder data divided by -1. It's because -4, because we use, if you remember, we use in the blog, we use 4 to stop the clock in 4 seconds. That's why we use -4. And the reason is minus is because the encoder is inverted. Okay, and also we need to calculate the WK in this lab. It's gonna be for each value. Remember, we need to calculate the WK for each value of the amplitude. So it's gonna be 60 times count per second divided by 4096. It's gonna give you for each.
That's the RPM.
Yep.
And it is 4096 because for the particular encoder that we have on these plants, they have 4096 slots per, or the count increases by 4096 every revolution. They may not necessarily have that many slots, but the count increases by that every revolution.
Okay, and after that we need to calculate the tachometer K. The tachometer K is gonna be for each value of the K. So K is gonna represent the each output in the system. So it's gonna be the mean of the data that we already saved in the tachometer output.
Yeah, and one more thing, if you are wondering where you get the variables Lab1 encoder and Lab1 tach, it's when you execute the load lines 15 and 16, which load the data, the file names, the mat files that you saved earlier using the earlier code, that will load your files, and these variables will get created in your workspace, and you can access those variables now like any other regular variable.
Okay, and after that we use, because we have already the data for each output of the encoder and the tachometer, we proceed to plot the two plots that we need in this lab for the linearity case. So it's gonna be the tachometer versus the WK, and also we need to plot the amplitude that we use versus the WK. So we just run the program. As you can see, the feature number 1 is gonna be the plot representing the tachometer versus WK, and the feature 2 is gonna be the amplitude versus WK. If you notice, it's kind of linear, right?
Yeah.
Because of the value, the voltage values that we use to get the output. After that, we need to calculate we need to use the polyfit function to calculate the slope of the K-tab. My friend Chayo is gonna explain you.
Well, what you do is polyfit is a function that fits a line to the data. So, fits a polynomial to the data. What we do here is we give the two vectors, that is your K-tach vector and WK vector, and since it's linear, the third parameter is 1 because we say it's a line. And polyfit returns you the coefficients in the order of the terms. So one of them is going to be the slope and the other is going to be the intercept of the line, and so basically polyfit is, in this case, is going to give you the slope. And as you can see in his code from his comments, the variable p gives you the slope and the variable s is the intercept.